So the next technique we're going to look at is this idea of partial fractions. So when we have an integral of some polynomial on some polynomial, so some rational function here. Now, first thing to do, if the degree of the numerator is greater than the degree of the denominator, do a polynomial division. Because then your fraction will become the degree of the numerator less than the degree of the denominator, which is what we really want. So then you factorise the denominator, and then depending on what you get, for every linear factor, create a fraction. So a over x minus a, for instance. And if you have multiple linear factors, so x minus a to the power of n, create a fraction for every power. The only other factor you could have, of course, is a quadratic. And so if you have a quadratic, then write a linear factor on top. Alright, so let's do this one. X squared on x plus 1, well, the bottom's already a linear factor. This is more, the point is the top, because x squared, so we do our polynomial division. And if you don't see it straight away, okay, let's do the division. X into x goes x, leave me a remainder of minus x. X into minus x goes minus 1, leave me a remainder of 1. So I can rewrite that as x minus 1 plus 1 over x plus 1. And everything there can be integrated. So we get x squared on 2 minus x plus the log of x plus 1. Now let's have a look at the next one. X squared minus x on the bottom. Well, that factorises to be x times x minus 1. So on the right hand side, I create a fraction for each of those factors. So I'll have a over x, b over x minus 1, and we know that's got to equal our integrand. What we're really doing is reversing our algebraic fractions questions. I mean, normally we see fractions added together and we create one algebraic fraction. So this is sort of decomposing it back to the original fractions that made up. Now, to do this, if I get rid of the denominator, so multiply everything by x, x minus 1, and that makes life a little bit easier, because we want to find a and b. Now, I could expand out and equate coefficients. Say coefficient of x has got to be the same as coefficient of x. Constant's got to equal the constant, that sort of idea. Or I could just substitute numbers in and try and work out what it is. Don't just pick any number, use sensible numbers, because if I choose x equals 0, the b goes away. So I'll find a straight away. And we get a is negative 3. And now, if I do x equals 1, the a will go away. And so I get b equals 3. Alright, so I now know I can rewrite this fraction as minus 3 on x plus 3 on x minus 1. And that we can integrate. So we get 3 log, or minus 3 log x plus 3 log x minus 1. When the coefficients are the same, well, don't worry about the sign, I'm talking about the actual number, then I'm going to use my log laws and bring that in. So it'll be 3 log x minus 1 on x, plus, of course, a constant. X plus 5 over x squared minus 3x minus 10. Factorise the denominator, and I have 2 linear factors. Again, so let's set it up. I'll choose negative 2, and that'll get negative 3/7 for b. And then if we substitute in 5, I'll get 10/7 for a. So this one, I suppose I could have factorised out the 1/7, because they're both over 7. But again, we end up with log functions, and of course we're going to get log functions. Because if we have a linear factor, we're always going to end up with a constant on top. And a constant on a linear factor, when you integrate, you always get a log function. So it's no surprise we keep getting these log functions. In this case, I didn't bother using the log laws, because one's got 10, the other's got 3. I suppose I could have brought the 10 in and made that x minus 5 to the power of 10, made that one x plus 2 to the power of 3, and then brought it all together. Nah. I don't tend to do that. I usually just, if the coefficients are the same in magnitude, then I'll bring them together. Okay, dx on x cubed plus x. So that one factorises to be x squared plus 1. Well, if I make x equals 0, the b and the c are going to go away. So let's do that. So a is 1. There's nothing to say I can't use complex numbers. If I let x equals I, then the a is going to go away. So I get minus b plus ci is equal to 1. Well, the real part must equal the real part, and the imaginary part must equal the imaginary part. So b equals negative 1 and c equals 0. So you might prefer to expand out and equate coefficients. Of course, you can always do that. So back to our integral. 1 over x, we have a log function. The second one turns out to be a log function again, because we've got x over x squared plus 1. And of course the derivative of x squared plus 1 is 2x. So I end up with the log of x minus a half the log of x squared plus 1. Notice I didn't bother with the absolute signs, because x squared plus 1 is always going to be positive. It doesn't matter whether, if you put it there, it's still fine, of course. X dx on x plus 1 squared, x squared plus 1. All right, a little bit more work to do here. So I've got a power of 2. So I create a fraction for both powers. So ax plus 1 plus bx plus 1 squared. And the other factors are quadratic, so I create a linear function on top. So I'll call that cx plus d. And here's the wonderful expression that we need to work out: a, b, c and d. What is going to be a sensible substitution to start with? Well, I think x equals -1 would be the logical first one to go, because that'll get rid of the a. It'll also get rid of the c and the d. So I'll find b straight away. So yep, sure enough, I did that first. So b is -1/2. What did I choose next? Okay. If I do x equals I, then the b is going to go away, and so's the a, because they will become 0. I get -2c plus 2di is equal to I. Real part must equal the real part. Imaginary part equals the imaginary part. So c is 0, d is 1/2. Well, I know what b, c and d is, so how about I just substitute in x equals 0, because I can't see a substitution that's going to make the other ones disappear. So if I sub in 0, I get 2a plus b plus d is 0. But we know what b is, we know what d is, and after all that, a turns out to be 0. So we now have -1 on 2 x plus 1 squared. Oh, we finally get one that's not a log. We've got x plus 1 all squared, so that's nice. That'll become, well, that's, if I was to do a substitution, that would be u squared on the bottom, wouldn't it? So we'll get a -1 on u. X squared plus 1 in the second fraction, that's going to be an inverse tan function. So we end up with 1/2 1x on x plus 1 plus inverse tan of x. Now, so I say, here I just did the substitution, u equals x plus 1. I didn't write it down. So I just had -1 on u, so it became 1 on u. There is an alternative way, which you're going to love, because it involves writing no working out. Okay. It's called, well, sometimes called the cover-up method. Okay. You have rewritten your fraction, and in this case they're all linear factors. So if you've rewritten it, we've ended up whatever the function was on top, but we're a plus b plus c. To find a, substitute little a, so whatever little a is, into function x, x plus b, x minus c. Now why it's called cover up, because it's like saying, I will cover up that factor, I don't want it. So it's like it's not there, and I'll substitute it into everything else. Then to find b, I do exactly the same. I'll cover up the x minus b and substitute b into everything. And then to find c, I do the same, and so on, and so on, and so on. So our first example, you'll remember, was a on x plus b on x minus 1. So a is -3, because I'm going to substitute in, so for a, well, I'm substituting in 0, cover up the x, and you get 3 on 0 minus 1. So a is -3. To work out the b, I'll substitute in 1, cover up the factor, I get 3 on 1, it's 3. Then we had this one, okay? So to work out a, I'll substitute in 5, cover up the x minus 5, I'll get 5 plus 5 on 5 plus 2. So 10/7. To find the b, cover up the x plus 2, and I'll get -3/7. So it certainly can be a lot quicker than the other way. Which is brilliant when the denominator is all full of linear factors. But some of those examples we've got quadratic factors. So what do we do? Well, with the use of complex numbers, you can still use the idea. Okay, so we want to do this one. Well, to find the a, again, I can just cover up, substitute in 0, we get a is 1. But to find the bx plus c, well, cover up the factor x squared plus 1, substitute in I. So whatever makes the denominator equal to 0, basically, is what we say. So I substitute in I. So I'll get bi plus c is 1 on I. So bi plus c is -1, b equals -1, c equals 0. So you can still, it's interesting, when I've seen this in books, they don't use it for quadratics for some reason. They only tend to stick with linear functions. Maybe it's because the linear function one's so easy. But it certainly works with quadratics as well. You just got to use complex numbers. However, sometimes the complex numbers might not be that easy. This wasn't one of our examples, but I'll use it to illustrate my point. Well, to find a, that's not a problem. I'll substitute in 1, and we'll get 1. But the next one, I'm going to have to substitute in I on 2. Now, what would make the denominator equal to 0? Well, if that was I on 2, then I'll get 0 on the bottom. So I'll cover up the 4x squared plus 1, but then I have to substitute in I on 2 into everything. Well, all right, okay. Whew. Eventually, I get 1 minus 3 on 2i, and I can say, well, the real part equals the real part, the imaginary part equals the imaginary part. So b is -3, c is 1. So whilst that cover-up method works beautifully for linear factors, some quadratic factors, like the first one I did there, fine, not a huge problem. There are other quadratic factors where you may have been better off using a different method. Going back and using the, oh, well, I'll just substitute numbers in. You might end up with simultaneous equations and you'll get it. What about when there were multiple factors? Again, it still works, just a little bit more work. So this one, oh, well, to work out A, that's going to be pretty quick. But B and C, you've got to be careful here. So let's work out A. A is -2. So that one's fine. It's the higher power you use the method for. So when I use the cover-up method, it's C that I'm working out, not B. Because over here, I'm going to cover up x minus 1 squared. It's the higher one. So it works nice for the higher one. I get 3. But what about B? Well, that's where I'm just going to go back to just substitution. So if I let x equals 0, I'll get that. And we're playing with that. I get -1 minus b plus 3, because we know c is 3, is equal to, and the right-hand side turns out to be 0. So b is 2. So it is useful to have like a whole tool chest of ways of playing with this. Because sometimes cover-up works beautifully. Sometimes, no, it's going to be too much work. I'll just do simple substitution. That'll get me the answer. Ooh, let's try this one. Okay, so the higher power in this case will find me the b. So b ends up being -1/2. Great, I've got that. Let's do the cx plus d, because I know that one will be simple. I'll just substitute in I. Mind you, the right-hand side, oh, it's not too bad, I suppose. Ends up being 1/2. So I've got C, I've got D, I've got B. I still have to work out A. That's where I'm just going to go, oh, well, the x equals 0. Let's see what happens. So A plus B plus D equals 0, but we know what B and D are. So A ends up being 0. What happens if the quadratic can't be factorised? So that x squared plus 4x plus 5. Well, A, again, A is going to be simple enough to work out. Cover it up, and I get 1. X squared plus 4x plus 5. What did we say? What makes the denominator equal to 0? So what makes x squared plus 4x plus 5 equal to 0? Well, if I complete the square, I'll work out that, I'll substitute in -2 plus I. So if I now substitute in -2 plus I get B times -2 plus I plus C is 2, or -2 plus I plus 1. We're getting a little bit of working out there. B's -1 and C is -3. Am I suggesting you do it that way? No. But again, I'm just showing you, well, the idea works. I probably would have been better off just finding other substitutions, create simultaneous equations and go from there. All right. So 4D is playing with this idea of partial fraction.